Hello and welcome to your career growth machine, QuickTechie.com. Let's take a look at this diagram. It's illustrating a crucial concept in Apache Spark: shuffle partitions and how they impact performance. Pay close attention, as understanding this can make or break the efficiency of your Spark applications. The scenario. The image contrasts two scenarios. One where a Spark operation is running smoothly. I got this. And another where it's struggling. This is too hard. The difference lies in the number of shuffle partitions used. Let's break down the elements. 1. My data, the input data. On the far left, we have my data. This represents the initial dataset we're working with. It could be data read from a file, like a CSV, Parquet, or JSON file, a database table, or any other data source supported by Spark. The format of the data isn't specified in the image, but it is not as important as the core idea that it represents the starting point of our Spark processing pipeline. Quote. 2. DataFrames. DF. The boxes labeled DF represent Spark DataFrames. As we've discussed before, a data frame is a distributed collection of data organized into named columns. It's like a table in a relational database or a spreadsheet, but spread across multiple machines in a cluster. 3. Partitions. Dividing the work. The rectangles inside each DF box represent partitions. This is a fundamental concept in Spark. What are partitions? A partition is a logical chunk of a larger distributed dataset. Spark divides your data into partitions to enable parallel processing. Each partition can be processed independently on a different executor in the cluster. Why are partitions important? Parallelism. Partitions are the key to Spark's parallelism. By dividing the data, Spark can process different parts of the data simultaneously, significantly speeding up computations. Data locality. Spark tries to process each partition on the machine where the data is stored, or close to it, minimizing data transfer over the network. 4. Shuffle. The data dance. The arrows connecting the DFs represent a shuffle operation. What is a shuffle? A shuffle is a physical redistribution of data across the network. It occurs when data needs to be regrouped based on a key. Common operations that trigger shuffles include group by, join, distinct, repartition. Any operation that requires data with the same key to be on the same partition. Why is shuffle expensive? Shuffle is a costly operation because it involves, quote, network I/O. Data needs to be transferred across the network between executors. Disk I/O. Data is often written to disk during the shuffle process. Serialization/deserialization. Data needs to be converted into a format suitable for network transfer and back. 5. Spark.sql.shuffle. Partitions. The key configuration. This configuration parameter determines the number of partitions that are created after a shuffle operation. Scenario 1. Left side. I got this. Partitions equals 7. This implies that the initial data, my data, was likely already partitioned into 7 partitions. The shuffle operation, represented by the arrows, maintains a reasonable number of partitions. The processing seems to be going smoothly because the workload is likely well distributed across the executors. Scenario 2. Right side. This is too hard. Partitions equals spark.sql.shuffle. Partitions equals 200. Here, the spark.sql.shuffle partitions property is explicitly set to 200. This means that after the shuffle, the data is divided into 200 partitions. The "this is too hard" message suggests that this is causing performance problems. Why is 200 partitions, in this case, too hard? Overhead. Too many small partitions can lead to excessive overhead. Spark has to manage metadata for each partition, schedule tasks for each partition, and so on. This overhead can outweigh the benefits of parallelism if the partitions are too small. Task startup time. Each task has a startup time. If you have many small partitions, the cumulative task startup time can become significant. Skew. If the data is not evenly distributed among the 200 partitions, you might end up with some partitions having very little data and others having a lot. This is called data skew, and it can lead to some executors being overloaded while others are idle. What's the right number of partitions? There's no one-size-fits-all answer. The optimal number of partitions depends on factors like size of your data, number of executors, amount of memory per executor, complexity of your operations, general guidelines. Too few partitions limits parallelism, Underutilizes cluster resources. Too many partitions. Increases overhead. Can lead to skew and performance degradation. Rule of thumb. A common recommendation is to aim for partitions that are around 100 to 200 megabytes in size. Start with a reasonable number, e.g., 2 to 3x the number of cores in your cluster, and adjust based on experimentation and monitoring. Concepts missing in the image. Number of executors. The image doesn't show how many executors are available. The optimal number of partitions is related to the number of executors and cores. Data skew. The image doesn't explicitly illustrate data skew, which can be a major performance bottleneck. Adaptive query execution, AQE. Spark 3.0 introduced AQE, which can dynamically adjust the number of shuffle partitions at runtime based on the actual data size after each stage of the query. In conclusion, this diagram effectively highlights the importance of choosing the right number of shuffle partitions in Spark. Too few partitions limit parallelism, while too many can introduce excessive overhead. Finding the sweet spot is crucial for achieving optimal performance in your Spark applications. Remember to experiment, monitor your applications, and adjust the spark.sql.shuffle.partition setting, or rely on AQE if you are on Spark 3.0 or later, to ensure your Spark jobs run efficiently.